Test, hello, test.
Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science, and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Hi, hello. Okay, good afternoon, everyone, and also good morning for the speaker. Right. Today we have the IF colloquium, right? And now we have the speaker, Dr. Timothy Davids, like he finished his PhD from Oxford University and then did a couple of like postdoc, and now he's a reader in Cardiff University, and his expertise in galaxy formation and evolutions and also HN feedbacks. And today he will talk about tracing out darkness with galaxy and then black holes.
Thank you very much. Yes, so I'm going to talk to you today about how we can use cold gas in galaxies to trace out the dark components of those galaxies that are important in affecting their evolution, but we can't trace directly with other forms of light. So we have to use dynamics typically to study those components. So what I'm specifically concentrating on for most of the talk are the centers of galaxies. So galaxies are complex and dynamic environments, and especially their centers. So their centers, the inner kiloparsec or so, have a lot of different processes ongoing, all of which are crucially important in understanding what's going on in those systems. So for instance, the middle of galaxies, that's where most of the star formation is happening. Most of the gas is concentrated at the centers of galaxies. And so a lot of star formation is happening in those regions. And those stars are putting energy back into the medium as they evolve and they die. And understanding how that affects future generations of stars is absolutely critical. We also, in the centers of galaxies, that has a very deep potential. So there's a lot of mass there. You have a lot of stars that already exist. You have a lot of gas. You have a lot of dark matter. You have the black hole. All of that means that the potential, so the strength of gravity in the center is very, very high. And so what that means is your rotation curve is steep and you get a lot of shear, so differential motions as the gas, stars, and everything rotates around the center of the galaxy. And so that can affect things as well. You've got a black hole that's sat down there in the center. That affects some region dynamically. That region is fairly small, but it can have other impacts as well. You have to have gas that flows inwards on towards that black hole. We know that black holes have grown over the lifetime of the universe significantly. We see their energetic output as they shine as active galactic nuclei. And so we know that we have to funnel gas from large radii in galaxies right the way down to their centers. And this inflow has to pass through that inner kiloparsec region. So studying how that gas is losing angular momentum to allow it to get into the centers of galaxies is absolutely crucial for understanding that process. That black hole can have other impacts as well. If it's swallowing material, then it outputs energy in various forms. And one of those is radio jets. That's highly energetic, relativistic plasma, so plasma moving close to the speed of light, that is ejected from the black hole around its poles and expands out into the medium very, very quickly. And those can have big impacts if they were to slam into a gas cloud. Let's say they were going to destroy and entrain and eject that gas cloud very, very quickly over time. That could cause outflows in itself, but those outflows could also come from the star formation or from just light coming from that black hole as its accretion disk is very, very bright. So you've got a lot of different processes ongoing in that region, and all of them are happening all at the same time. And so galaxy centers are really a crucial laboratory which we need to probe in order to understand the interplay of all these processes. So I've got three big questions that I want to try and address in this talk. And the first one of these is black holes. So why do supermassive black holes, those black holes that are greater than 1 million solar masses in size and live in the centers of galaxies, why do they care about the galaxy that they live in? Second up, I'm going to address what is the role of cold gas, so the material that is very cold and very dense, in fueling black hole activity. It's not a clear-cut picture, and we need to investigate that further. And then finally, I want to ask the question, does living in a deep potential well, like you have at the centers of galaxies, change the structure of the interstellar medium, so the gas in galaxies? And if so, how does that affect their star formation? So those are my big questions for this talk. So the probe I'm going to use to do this, typically throughout this talk, is the coldest gas that exists out there in the universe. And that's the molecular interstellar medium. So this is gas, mostly hydrogen, that is so cold and so dense that it is able to form molecules in space. So typically H2. This gas is sitting out there in space at only 10 or 20 degrees above absolute zero. And this material is abundant, but it's very hard to trace, actually, that H2, the molecular hydrogen, because that molecule doesn't have a permanent dipole moment. It doesn't emit very well in light that we can see. It really needs to get hot to 500 or 1,000 Kelvin before it starts to emit light that we can observe from Earth. So we can't trace that H2 directly. So instead we have to use tracers, and the one we typically use is carbon monoxide, so CO. It's the second most abundant molecule because there's a lot of carbon and a lot of oxygen out there. You might wonder why not CO2? We're much more familiar with that from here on Earth, but there's not twice as much oxygen out in space as there is carbon. And so while carbon dioxide exists in space, most of the gas is in the form of carbon monoxide, CO. And that's nice because it has a permanent dipole moment, so it emits light that we can observe from Earth. That light comes to us at sort of millimetre frequencies, so at 3 millimeters, the first transition, 115 gigahertz. And that's an area of the atmosphere that we can observe through. It's an opaque window in our atmosphere that's not blocked by water vapor, for instance. And so we can observe that from the ground using telescopes here on Earth. And the really great thing that I'll use in this talk is that this molecular gas provides a dynamical tracer. You can see how it moves because you're observing an emission line. Emission lines in quantum mechanics have a very specific frequency that they are allowed to emit at. And so as you see that Doppler shifted as the gas moves towards or away from you, you can tell how that gas is moving along the line of sight. And so you can use those kinematics to trace out how the gas is moving. So my first question then, black holes. I've said here that they care about the galaxy that they live in. So what do I mean by that? Well, we know black holes are important in galaxy formation. We have a set of observations that tell us this must be so. For one instance, if you look at the color magnitude diagram, so you see that in the bottom here, if you plot color here, so whether a galaxy is blue or a galaxy is red against its mass, you see that there are two distinct regions here. There is a blue cloud, and this is where spiral galaxies like the Milky Way like to live. Then there is a red sequence, which is a surprisingly tight sequence of galaxies that are elliptical or lenticular, so these red, blobby, fairly smooth galaxies. And we know that galaxies are red because they are no longer forming many stars, and galaxies are blue because they're forming lots of stars. This is because massive stars are blue, but they're also very short-lived. And so as they die away, galaxies have to become redder. If you wanted galaxy formation and evolution to get rid of star formation in galaxies to create these ellipticals just on its own, without the impact of anything quick, you wouldn't expect to have the gap we see here between these two things. This is called the Green Valley. And there are galaxies there, but they're quite few and far between. And so the argument is that at least some fraction of galaxies have to move over this space quickly. They have to have all their star formation stopped. Bam. And one really nice way to do this is with accreting black holes. This is because liberating energy from black holes is really, really efficient. You get a lot of energy for every kilogram of mass that you throw into a black hole. Depending exactly on the spin, etc., you can get almost half of the rest mass energy back out when you throw mass onto a black hole. And so that's the most efficient way of generating power in the universe. And so we have a lot of energy available in those black holes, and there's a lot of mass that we know they've built up over time. So we think this mass has been built up as they accrete and then feed back on their galaxy and stop it forming stars. And we see the impact of that on the black hole properties. So here I'm showing the famous M sigma relation. So this has the mass of the black hole on the y-axis and the velocity dispersion of the galaxy, or you can think of it as galaxy mass, on the x-axis. So as galaxies get more massive, they have much bigger black holes. So up here, you have things that are 10 billion solar masses in size. And down here, you have things that are only 1 million solar masses in size, like our own Milky Way black hole. And these galaxies almost always have a black hole in their center. And that black hole knows about the galaxy that it lives in because its mass depends on it. But that's weird. If you think about it, although these black holes are very massive, the area that they can actually affect gravitation is really quite small. Even for something up at 10 to the 9, you're only talking about 10-ish parsecs, 10, 20 parsecs at max, where its gravitational pull is actually dominant over the gravitational pull of the galaxy as a whole. So really, that black hole shouldn't know anything about the galaxy at large, and the galaxy shouldn't know about the black hole. They are, yes, massive, but they work on very different scales, and so they shouldn't communicate, really. But this diagram shows us somehow they do. Now, you also see this picture about quenching on this diagram. So here, these authors, McConnell and Marr, looked at the quenched galaxies, so those that live in that tight red sequence I described. And those are the red points here, the red and the green. And then the blue points are those star-forming galaxies. And the red and blue lines are the best fit for the black hole masses of those populations separately. And you can see that the galaxies that are still forming lots of stars today have smaller black holes at fixed galaxy mass than those that are quenched. So the red points. That suggests that this picture that I painted earlier could be correct, that you throw more mass onto a black hole and that ends up quenching that star formation, stopping star formation. But you should be worried a little bit about this result because you see the different symbols. Those are different methods for measuring the black hole masses. And you can probably see by eye that most of the star-forming galaxies, the blue points, are one type of symbol, typically the triangles or the round symbols, which are masers, which are like microwave lasers, and gas. Whereas most of the red points are stars. So these black hole masses have been measured using the dynamics of the stars. And whenever you see a systematic offset between populations that has been measured using the same different technique, you have to worry, is this a systematic difference between techniques, or is this result real? And so it would be really nice to find a method of measuring these black hole masses that works in all galaxy types and at all masses to really put this to bed. Is this effect real? So that's what we set out to do. So what we would need is a tracer that is dynamically cold, so i.e. it's responding to the gravity of the galaxy and not a lot else in all galaxy types. It has to be present to the very center of that galaxy, and it has to be observable at high angular resolution so we can get a zoomed in view of the center of that galaxy. And what I'm going to argue here is that molecular gas is a great way of doing this cold carbon monoxide material, for instance. So this gas is present in about 1 in 5 of these quenched galaxies. And that 1 in 5 is essentially random because most of that material is brought in from outside. It's pretty randomly distributed. And it's basically there in all of the spirals. And so we should be able to get a good representative sample of both populations. It has a low velocity dispersion. It's very cold gas. It's sitting there at 10, 20 degrees above absolute zero. So it doesn't move a lot on its own. It's mostly sitting there and rotating around in the potential. And with telescopes like ALMA, the Atacama Large Millimetre Submillimeter Array in Chile, you can get very high resolution, for instance, about 10 milliarc seconds, or even a little bit higher, depending on what you observe. So this fulfills all of those criteria. So we set out to try this. And this is where my survey called WISDOM comes in, Millimetre Wave Interferometric Survey of Dark Object Masses, where we're aiming to do exactly this. So these details are a little bit technical, so I'll just skip over those. But if anybody is interested, there's the website there, wisdomproject.org. So how does it actually work? So here's an example for you. Here is one of these big elliptical type galaxies, NGC 383. This galaxy is an elliptical, but you see there's a little smudge in the center of that galaxy there in this ground-based image. And when you observe that with the Hubble Space Telescope, you see that this is a little disk of gas and dust. You see here highlighted in this Hubble image. And we know this galaxy has a big black hole in the center because it has a huge radio jet. It's a big radio galaxy. It's outputting that relativistic plasma that we talked about at the beginning. And you see here in the purple, this is X-ray emission, so very high frequency light. And from a space-based telescope, you see that this jet is even picked up in these X-rays as this jet blasts out of that galaxy at close to the speed of light. So we know there is a big black hole in the center of this system. And we know there's gas around it from the presence of this dust disk. So this has been observed before in the carbon monoxide molecule. So these are observations from O'Connor-Flacker et al. At about 2 arcsecond resolution. You can see here there's definitely gas in this disk, which is nice. So we went and observed this disk with ALMA. So this is what we got. Now we're looking at the gas at about 40 parsec resolutions. That's about 120 light years is the size of our resolution element. And you can see beautiful structure here. This is a wonderfully regular disk with some spirally ring type structures overlaid on it, but it's just beautifully regular. This is a paper by North et al. That I'm describing here, one of my ex-students. We've actually got even higher angular resolution now. So this is a sneak peek. Nobody else has seen this really at much higher resolutions. So now we're talking about 30 light year resolution. And you can see here, this just starts to break up. You see that ring/spiral structure that we talked about coming up even more cleanly now in this even higher angular resolution map. And this is a paper that's in prep by Zhang et al. So the really nice thing is this black hole in the center of this galaxy is directly visible. So what I'm showing you here is the velocity field. So whether the gas is coming towards us in red or going away from us in blue. You can see this beautiful red-blue pattern that's regular rotation. But you see, as you reach the center of the galaxy, rather than the velocity dropping to 0, as you might expect, it gets higher and higher and higher. You can see that even more clearly if we extract a pseudo-slit from this data. So we extract how the gas is rotating along that strip. And that's what you see here. So this is called a position velocity diagram. So I'm showing you the position along that slit. So 0 is the middle, going outwards on each side. And you can see where the gas is, what velocity the gas is rotating at as a function of position along that line. And if this galaxy had no black hole, you would expect it to be high on the outskirts and then drop to 0 in the middle. But that's not what you see. It stays high and then it gets even higher. And this is gas rotating faster and faster and faster and faster as it rotates around that black hole in the center of this galaxy. So this is really easy to measure the black hole mass of, because what you get in this very center is a Keplerian curve, that square root gm over r that you get from Newtonian gravity as the gas rotates around this black hole. Obviously, as you get very, very close, you're going to start having relativistic effects. We're not in that regime yet with these observations. From our very high angular resolution data, you see this even more beautifully, that Keplerian rise in the center here. So this is just stunning and will be essentially the most accurate black hole mass measurement ever made, I'm sure. So what we do is we model this data. So you're a theoretical center. So modeling is something I imagine that you're all quite familiar with from what I heard at the beginning. And so we have to model this data to make sure that we're treating all the observational effects well. And I do that with this tool called Kinemis. And there's a website there if anybody is interested in using this tool for measuring your own dynamics, kinematics. But it's technical, so I'll skip over this a little bit. So we can measure that black hole, and that black hole in that galaxy is about 3 billion solar masses in size. So really quite a large black hole in that quite large galaxy. So that's one example, but we don't have to just do this in the massive elliptical type galaxies where the black holes are large. We can also do this other places. So this is NGC 404. This is a dwarf elliptical galaxy. So it is still elliptical, but it's really a quite tiny galaxy. And this is very close by to us. It's only about 3 megaparsecs. It's about 12 million light years away from Earth. And you can see, if you zoom in the very center of this galaxy with the Hubble Space Telescope, you see these dusty structures that tell us there's definitely gas down near the center of this galaxy. It was observed in the past. You see this image on the right that's just a blob, but with the ALMA telescope, we went out and observed this, and now we have observations at half a parsec. So that's 1.5 light year resolution. And that is just stunning. You see here individual clouds of gas as they rotate around the center of this galaxy. There's this ring structure here, and then a one-armed spiral that loops in. And the black hole doesn't actually lie at the center of this loop, as you might think. It lies in the center of this dense little disk down here. The gas is spiraling onto that disk and feeding that central black hole. And we can measure the mass of that black hole, and it's only about 5 times 10 to the 5 solar masses. So it's not even 1 million solar masses, only 500,000 solar masses. So it's very low mass. And with this technique so far, we're really starting to make a difference. So you see the red points and the blue point here are all these sort of molecular gas measurements that have been done by either our team or the other teams that have sprung up to use this method after we pioneered it. And you can see we're really starting to make a difference in constraining the black hole masses of galaxies across the Hubble across this diagram, and being able to start to answer that question of why the galaxies care about that black holes. So I can't tell you yet exactly why galaxies care about their black holes, but we're making progress, and molecular gas can help with that. We need wisdom and programs like it to do this. And there are actually a lot of galaxies we can do this with. ALMA is a wonderful machine for doing this. And so we really hope to have build up the samples we need to answer this in the coming years. So the next thing I want to look at is what else is going on in the centers of these galaxies that can help us constrain this. So in addition to the molecular gas, we also detect continuum emission in our objects. So that is emission that's not a line anymore. This is some form of continuum, so emission that is at all frequencies. And this wasn't really expected. So all of our targets have an unresolved, so a point source of emission that is smaller than 5 or 10 parsecs. And so there are very limited things that this could be. We know that black holes are supposed to have dusty donuts around them that are called the torus, but these shouldn't emit this much light at these frequencies. It could be emission from electrons within star-forming regions, but again, there's too much emission. It doesn't work. You don't have enough energy available. And it could also be light from these jets, but it, again, doesn't match the expectations. If you look at lower frequencies of these galaxies where this synchrotron emission, these electrons spiraling around in those jets, you get much more emission than you'd expect by extrapolating those. And so we don't think it's any of those things, at least not optically thin, large-scale emission. But we find that if you look at the fluxes of these, they correlate very strongly with the black hole mass. So here it's about 0.5 Dex, so reasonably strong, but not crazy strong. And so you can actually measure the mass of the black hole directly using this continuum emission, which is quite exciting. Even more exciting is you can tighten this up. So if you take also the X-ray emission, so the emission in high frequency light, you find that these actually form a plane. So you can combine these. If you take both the X-ray and the millimetre light, you get a correlation that's only has a really small scatter, about 0.3 Dex. So you can measure the black hole mass relatively accurately just from these fairly simple measurements. And that's really quite exciting. especially because this correlation, you can predict it actually using models that work for black holes that aren't swallowing much material. They are low luminosity, and those you can sort of explain this. This light is from material that's puffed up around the black hole and is accreting quasi-spherically. It's the plasma there is optically thick, so the light can't escape. The energy is trapped, and that all gets advected onto the black hole, so moved onto the black hole, and the black hole swallows a lot of the energy, and those would produce a lot of light in the millimeter, and we would then get a correlation like this one. But we find that this correlation also holds in galaxies that aren't like that, those that are swallowing a lot of material. And that's weird, and we don't understand why. And there's a lot of work going on to this Bass sample here. You see that there's more scatter. Part of that is that their black hole masses aren't as good, aren't as well measured, but they seem to lie on the same relationship. And that is strange, and we don't understand that. So watch this space for that. So I'm going to skip over this because it's fairly technical. So molecular gas can help us with this question, but so can this millimeter continuum emission, and that's really quite exciting. And this is all very new stuff, came out this year, so watch this space on that. So cold gas and AGN fueling. We have these black holes in the centers of galaxies that we talked about in the last section. We know that some galaxies, those black holes are swallowing a lot of mass, and some are swallowing very little. And these are typically thought to have been set up because the fueling is different. So those things that are swallowing very little gas, it's probably material that's actually quite hot. It's plasma at 1 million degrees that it's swallowing very slowly. Whereas black holes that are swallowing a lot of material, maybe they encountered a dense cloud of cold material and they're swallowing all that up very quickly. Excuse me. But there are various challenges to that picture, in that if you look at these systems that are supposed to be fueled by hot gas and you map the cold medium around them, you find there's a lot. So almost all of these galaxies, when you zoom in on their centers, they have these disks of cold gas around the black hole. And so it's possible that this paradigm is wrong, that actually these things are getting material from the cold phase, they're eating that material to fuel their activity, just at a lower rate for whatever reason. And so we wanted to investigate this. There are global correlations, certainly between, for instance, the power of jets, we see plotted in the x-axis, that are output, this relativistic plasma flowing out of the black holes, and the amount of cold gas available. At global scales, that presence is there. But it's always hard to know with these sort of correlations whether this is just big things are bigger. You know, you've got a bigger black hole, so it's easier for it to output more power. That could be the cause of this correlation. Or it could be that the more gas you have available, the more that black hole can eat. And so the bigger it gets and the higher power jet it puts out. And we need to know which one of those that is. So our sample contains a lot of these active galaxies, although it wasn't selected for them. They just are there because those types of galaxies are common. So our sample is a great place to have a look at this and see, in normal galaxies, not selected because they are bright in a specific waveband as AGN, what correlations exist between the molecular gas in the middles of these systems, right around the black holes, and the nuclear activity from those black holes. So what we can do is we can take our beautiful maps of the gas in these galaxies. So here's 3 examples, and we can put down apertures and say how much gas is within these. So this is a paper by Alfred et al. That says submitted there, but it's actually been accepted now. It's 2014. And we can have a look at the activity of these black holes, traced both by X-ray emission, so this very high energy light, emission from oxygen that's excited by the black hole, and the power of those jets that are being output that you can trace using radio data. And we can combine them with these cold gas masses estimated around the black hole. And what we find is that there's absolutely no correlation. So these previous studies that showed that there are these correlations between the amount of mass and the black holes, if those were because of fueling, you would expect them to get stronger as you go to smaller and smaller scales, because you're more linked time-wise. If the gas there is going to accrete very soon, it should correlate better with the amount of material that's being emitted, and we don't see that at all. These are just scatter plots. This is unexpected. We did not expect to see it. So the first one here, this is the X-rays. The same is true in the radio. So it seems that presence or absence of fuel on the parsec scales that we're probing, so the light year scales around the nucleus, does not predict current AGN activity. So how bright that black hole is at the current time. The accretion rates and the cold gas mass do not seem to correlate directly. Now, it's always hard because the time scales here are important. Although we're measuring on light year scales, it still takes many years to get that gas to fall in from those sorts of scales down to the black hole center. And so if it could be that the mass was there a million years ago, but we just can't observe it because that's now been swallowed, and the black hole's about to drop in activity, and so that creates the lack of correlation that we see. What about ISM structure? It has been seen in a lot of very active star-forming galaxies that the black holes are warped, so the gas that's flowing onto them is at a different angle than the gas that flows in the galaxy disk. And we see these types of things, these warps. So you can see these are velocity maps, again, red shifted and blue shifted material in each of these. And the green is the line of zero velocity. And you can see if you trace out that green line with your eye, you can see these ones on the left, they have a warp. That is not a straight line. It's an S shape in the centers of these systems. Whereas the ones on the right, that's just a straight line. Their disks are unwarped. About 25% of our galaxies have these warps. They tend to be in lower mass galaxies. But these don't seem to correlate with any of the traces of AGN activity. So it's not just that warp disks help material flow onto the black hole. They can be there, but they don't correlate with the AGN activity in a clear way. What we do see is an interesting correlation here, or lack of correlation, you could argue. So what I'm plotting here is this X-ray luminosity, so the amount of light coming out of this black hole, how active that black hole is at the present day. And I'm plotting that as a function of the concentration of this gas, so how much gas is piled up in the middle versus at larger scales. So this is the ratio of the surface density is measured at 50 parsecs to 200 parsecs. And so if you are a high number here, you've got a lot of gas in the middle. And if you are low here, you've got more gas on the outskirts. And what you see here in red was a previous study. And they found this very clear correlation where you have lots of gas in the middle of galaxies until you get very active black holes when this falls off a cliff. And this, they argued, was the black hole blowing that material out, destroying it, and creating a central hole in the galaxy. If you put our systems on here, though, they scatter all over the place. And so the question is, was this previous correlation wrong? There's no reason to think it should be wrong. It's a fairly simple measurement to make. Or are we actually observing a cycle here? Oops, sorry. Are we seeing these things were selected to be very active AGN at the present time? So are these the outskirts of the correlation, the envelope of the distribution? And galaxies actually flow along this line. They compactify, they get lots of gas in their middles. So they come along here, the AGN starts to turn on, and then at some point it gets bright enough and blows out this material, and then it turns off, and these galaxies flow backwards across this diagram to lower X-ray luminosity as their black hole turns off, and that allows them to then slowly build up their central reservoirs again. So we could be seeing part of a cycle here, but I'll watch this space for that. And there's another paper by Garcia Barrio that we worked with them where they try and explain this in terms of this cycle. So if you're interested in that, go check that out as well. So we find that the presence or absence of this fuel on parsec scales around black holes doesn't seem to correlate with AGN activity at the current day. So time scales are going to matter. And this ISM structure is not predictive, but it could indicate a cycle that's going on in these systems. So moving on to the final part in the last 10 minutes or so, what does living in this deep potential well do about the structure of the interstellar medium and then the star formation arising from it? With the Wisdom server, we have these beautiful maps of the gas in these early type galaxies, so these quenched systems, these red sequence ellipticals and lenticulars, and also in spiral galaxies, the blue cloud galaxies like our own Milky Way. And if you look at gas distributions just at the top here and at the bottom, you can see by eye they look different. The top ones are pretty smooth, and the bottom ones are very clumpy. There's a lot of spiral arms, etc. You might say, well, Tim, you've selected spirals and early types. Of course, the spirals are going to have spiral arms. But here we're looking in the inner kiloparsec or so. And the inner kiloparsec or so is deep within the bulge of these systems. So the potential there is fairly round. It's not clear that they have to have spiral structure going all the way to their centers, right? The potential is fairly similar in shape in both of these types of systems in the inner kiloparsec. So it's not clear that that has to be the case. In our early types, those gas disks are typically smooth. They can have central holes. They're lacking in large clumps. So the molecular clouds in these systems seem to all be quite small. There's not a lot of density contrast, and there's a small distance between these clouds. It's a more continuous medium. And in the spiral late type galaxies, we see the opposite. They're clumpy. They're really clumpy, broken up into large clumps. And this is strange, and so we wanted to quantify this and also check out what happens by comparing to simulations. As a theoretical institute, you'll know the power of computational modeling. And so we ran a couple of simulations. This is with someone who was a student, now a postdoc in Dergencio. So what she did is she took a galaxy that she has simulated, idealized simulation. So she put in the dark matter halo, she put in a gas disk, and she kept those identically the same. Then she put the same amount of stellar mass in, but changed how it was distributed. So on the top left, she just put that mass in a disk, just like a spiral galaxy disk. And you can see that the structure of the gas in that galaxy became very flocculent, very spirally. As she increased the central bulge, so the concentration of that stellar mass towards the center of the galaxy, you see, as you go from the top here down to the bottom right, she's increasing that concentration, that bulge of that galaxy. You can see that the disk starts to get very, very smooth in the center, just like the ones we were seeing. So that seems to be, we're seeing the same effect in these simulations. So what we wanted to do is quantify this. And so we went out and we used some statistics that are typically used by optical astronomers when they're classifying galaxy mergers, for instance. These are also stats that are used in things like economics. So the Gini coefficient is one of these, which is essentially the fraction of bright versus dim pixels. Symmetry, so symmetry is just you take your image of your galaxy, you rotate it 180 degrees, subtract away the rotated one from the original one, and you look at the magnitude of the residuals. So if something is symmetric, you'd get a very low number. If something is asymmetric, you'd get a high number. And then smoothness. So what you do there is you take the image, you convolve it with a Gaussian of a given size, subtract it away, see how much flux is left. So if it was very smooth, you'd get a low number. If it was very not smooth, very clumpy, you'd get a high number. And so we measured these for all our galaxies. For the spiral galaxies from the FANGs, which is a big survey of spiral galaxies at sort of 100 parsec resolution. We used all their data as well. And we compared to these simulations from Indra, which are the green points. FANGs are blue, open circles. Our early types are red, and our late type spiral galaxies are in blue. And what you can see is that we've got strong correlations here between these parameters. So Gini and asymmetry are basically trying to measure the same thing, how clumpy gas is. And so you see strong correlations between those, but also the smoothness parameter, how smooth the gas disk is. And you see that the red points all have low smoothness, low Gini, and low asymmetry. So the gas is symmetric and smooth and not clumpy, whereas the spiral galaxies are higher in all of those things. And these simulations span that full range in the way exactly expected. So these things seem to be tracing the same thing. So what's driving this? Why is the gas structure different in these early type galaxies from the late type galaxies. We can have a look. We see that effectively the potential well depth is the strongest correlation. So here I'm plotting the stellar mass of the galaxies. So you have the spiral galaxies up here. The lower mass they are, the more asymmetric, the less smooth, and the more clumpy they are. And as your galaxy increases in mass, you become smoother, more symmetric, less clumpy. Velocity dispersion, again, I said that correlates with mass, so you see the same thing, we just have a smaller sample. The strongest correlation we have is here with this mu star. What's mu star? It's the stellar mass surface density, so the amount of mass divided by the radius over which you are measuring that amount of mass. So essentially here in the inner kiloparsec. So how densely the stars are packed in the center. So this potential well depth, because that correlates strongly with all of these measurements. So you can just see this effect by eye if we plot the maps of our galaxies on this space. So we have this stellar mass surface density, so how densely the stars are packed in the middle of our galaxies, versus this Gini parameter, so how clumpy they are. And you see by eye this effect, right? They are really clumpy up here, and they're really not clumpy down here. And so you can really just see the effect we're describing by eye. It could be, you might argue, that, well, what happens if this is all due to star formation, right? You get more gas in the centers of galaxies and spirals, perhaps, and then those have supernova, those blow holes in your gas distribution. They create a clumpy medium. We do find a correlation with surface density, but it's the opposite of that. The smoothest ones have the highest surface density, so we don't think that's what's going on. What we also find is there is some correlation with the star formation properties. So here I'm plotting the star formation rate, the specific star formation rate. So this is the star formation rate per unit stellar mass, and the star formation efficiency. So the star formation rate per unit gas mass. These first ones, there is a correlation, but only in that the early type galaxies have low star formation rates, which is by selection. So those aren't interesting. The star formation efficiency correlation is interesting, but we don't think it's causative. We think that actually this is the other way around. So why is this? Well, effectively, it comes down to how stable that gas disk is against collapse. So if you have a gas disk in a galaxy, it's rotating around, there's a fight between the centrifugal force that's trying to throw material out and gravity that's trying to pull it together. And you can quantify how important this is. And we know that both the stars, so the stellar mass, because that contributes to pulling the gas material in, and the gas mass itself, that obviously its own self-gravity could matter, those are in competition. And what we find is that in almost all of our early type galaxies, apart from this one weirdo, the stars are completely dominant in terms of which of these, the Toomre Q parameters I'm comparing here. So that comes from classic analysis by Toomre. But essentially, all you need to know is that it's whether the stars or the gas are going to dominate the stability of this disk, its ability to fragment and form stars. You see that the stars dominate in the early type systems, and many of the spirals actually as well. But the lowest mass, the lowest concentration ones, the gas starts to dominate. And so those are going to be able to fragment much more. And turns out what's really important is shear. So this is a little bit complicated, but effectively what happens is that if you imagine shear, what happens is if you've got a cloud and it's rotating, but it has some physical size, that means it's going to be rotating faster at one end than the other, because one end is closer to the center of the galaxy than the other. And that's going to have the effect of pulling that cloud apart. Now, if that cloud is massive enough, it doesn't care, because its own self-gravity will hold it together. If, however, it's not massive enough, the shear will win, and that cloud will be shredded. And what we show is actually that as you go into that deeper and deeper potential well, that shear effect starts to dominate more and more and more. So you have to be really quite dense. So as shear increases, which is this measured by this Alt A parameter, So as it increases from 40 to 400 to 4,000, which is a value that you can find in the centers of these galaxies, you find that only very dense clouds, I'm plugging density here, versus ratio of their random motions to the radius of these clouds. It's a bit of a confusing parameter space, but it's just the best parameter space to see this in. Effectively, what you can see is that this creates this step here in density. So only clouds that are very, very dense and therefore small can survive in a high shear environment. So we think that's what's going on. This, in the centers of these galaxies, the deep potential well is shredding all the big clouds. So you've only got small little clumps of dense gas left that are embedded in this smoother medium, because you've only got these small dense clumps and then the shredded remnants of the rest of the clouds. So molecular clouds feel the effect of these deep potential wells caused by these large bulges. And it's very likely, if you're going to shred up the fuel for star formation, that you're going to affect the star formation rates as well. You have less gas that is bound, and therefore less gas that's available to form stars. So this isn't just a novelty that affects just the interstellar medium. It's going to affect the future of these galaxies and how many stars they're able to form inside those bulge regions. So those are my conclusions from each section of the talk, and I'm really happy to take questions as people have them.
All right, thank you. So for the audience here, do you have like any questions? I'll just check it, and we don't have questions from YouTube and Facebook yet, but I do actually have questions because I'm curious why like the ideal tracer should have to be cold, right? I think hot tracer could be equally like important as a tracer.
So yeah, every tracer is good. You want to combine them ideally. The problem with hot tracers is that they have a lot of their own motion. So they have a large velocity dispersion. So for instance, if you go to the ionized gas lines, so the lines like H alpha, the ALMA series lines from hydrogen that are excited, 4,000 or 5,000 Kelvin, those lines have substantial velocity support. So they have their own motions of 30, 40, 50, 60, 70 kilometers a second. And you have to model those in order to take them into account. And you have to make assumptions about those, which we don't actually know all the answers to. And so the hotter your tracer gets, the harder it is to get back to what the real rotation is versus this effect. It's called asymmetric drift from the hot tracers. And so, yes, all of those tracers are important and we should be using them all. But dynamically cold tracers are really useful to get back at the potential more directly.
Okay, and what is specialty about the carbon monoxide? Because like many of the paper from JWST, they use like many different tracer like oxygen, nitrogen, but why do you pick carbon monoxide as your like tracer?
Yeah, so the material that we want to look at, as I've argued, we want it to be the coldest material. So that's sitting at 10, 20 Kelvin. So you need a line that is excited at those temperatures. So all of the lines that JWST sees are much hotter than that. JWST can actually see the H2 molecule directly. There are H2 lines in the JWST bandpass, but those are lines from material at 1,000 degrees or so. And so that's very hot molecular gas that's probably about to be destroyed, just been shocked, just been heated by a new star forming. And so it's only a tiny, tiny fraction of the mass. The typical mass that's tracing is a few thousand solar masses, whereas we want to trace the bulk of the material that's cold and dense. And so we need a tracer that's excited there. And carbon monoxide is the brightest of those tracers that we can observe easily from the ground. There are other tracers like atomic carbon that could be good, but unfortunately, they fall in a part of the atmosphere that is opaque to us. And so they have to be done from space with far infrared telescopes. Currently, we don't have a far infrared telescope in space. And so we are stuck with that one for galaxies at low redshift. that line redshifts, of course, so you can do it at high redshift using that line. But yeah, so carbon monoxide is the brightest tracer left in that cold material.
Okay, thank you. Just some general questions because I'll be interested in your like wisdom program. Can you tell like the audience what it is?
Yes, this is a survey where we have observations of about 45 galaxies, from dwarf galaxies to spiral galaxies to massive elliptical galaxies in the carbon monoxide transition. These are all objects that were selected to have regular dust disks in their centers and have bright molecular gas. And we have observations at sort of between 50 and 0.5 parsecs resolution, depending how big that black hole is, basically how far we pushed ALMA to observe them. And we have our first data release live on the website. So if playing with very high angular resolution maps of the molecular material and other galaxies is something that excites you, you should go to the website and check it out and download our data and use it. Always happy to help support as well. And so that data is all available and people can play with it. And if they need anything, they should drop me a line.
I'll be happy that the data is all public, right? Okay. Okay, thank you for the speaker like, again.
Thank you for having me.
Okay, so that's the end of the colloquium now.